In this video, we look at a modification of exercise 7 from the Larson Calculus 10th edition text from section 2.6. 2.6 is about related rates. So we're told that y is equal to tangent of x, and x of t and y of t are differentiable functions of t. So we've got x of t and y of t are the coordinates of some point, and those points are on the curve given by y equals tangent of x. Then we know that the rate of change of the x-coordinate is related to the rate of the change of the y-coordinate. And when we say the rate of change, we're referring to the time rate of change of x and the time rate of change of y. Those have to be related to each other. We're asked to find dy dt at these three x values, and I think we're also given dx dt. In the problems statement, we're given that dx dt is equal to 3 feet per second. Okay, so we imagine that we're measuring x in feet and y in feet, and we're on a curve given by the equation y equals tangent of x. So we know what that looks like. Roughly, it looks like that. Tangent has vertical asymptotes at all of the odd multiples of pi over 2. It has a tendency to repeat itself. So from negative pi over 2 to pi over 2, it looks like that, and then it repeats itself from pi over 2 to 3 pi over 2, and then 3 pi over 2 to 5 pi over 2, and so on. And we're asked to find dy dt at these locations. Now, this is 1/3 of negative pi. So if this is my y-axis, that tangent is going to equal 0 at 0 and negative pi and 2 pi. It's equal to 0 every time the sine function is 0 because tangent is sine over cosine. A little bit cold, so my handwriting is a little different than usual. But this is 1/3 of that, but then it's to the left of the y-axis. So this is negative 1/2 of pi. So I'm going to be at 1/3 of that. So approximately this is pi. So here-ish. That's when x equals negative pi over 3. And then x equals 0. We're here, and at x equals pi over 4. It's halfway to pi over 2. We'll be here. And the question is, okay, what is the rate of change of y with respect to t at those locations? It's relatively easy to find. We know that y is equal to tangent of x. And we know that x and y both depend on t, so we can differentiate both sides implicitly with respect to t. The derivative of y with respect to t is unknown. That's actually what we're looking for, so we're just going to call that dy dt. And the derivative of tangent of x with respect to t requires the chain rule, or implicit differentiation, same thing. We take the derivative of the outside function evaluated at the inside. The derivative of tangent is secant squared. And you substitute your inside function back in, so that's going to be x of t. And then we multiply by the derivative of the inside by the chain rule. So this equation tells us how the rate of change of y with respect to time and the rate of change of x with respect to time are related to each other. It actually says that the rate of change of y with respect to time is the secant squared of the x value times whatever the rate of change of x happens to be. Now we are given that dx dt equals 3 feet per second at those particular locations. So we can just substitute in dx dt equals 3 there, and then substitute in these x values to get dy dt at those locations. It's very simple. So we just substitute in negative pi over 3 here and our x prime, that's derivative with respect to t, which is 3. And then we substitute in x equals 0 here, and we substitute in our x prime, which is 3. And then we substitute in x equals pi over 4 here. And then we substitute in the x prime dx dt, which is equal to 3. Now, in order to find those, we can look at the graph of the secant function if we want to, or I actually prefer to think of it in terms of cosine. I like to draw triangles in the xy plane. So for negative pi over 3, talking about a triangle that's down here. So we go pi over 3 units in the clockwise direction relative to the x-axis. Pi over 3 is 180 divided by 3 degrees, so it's 60 degrees. So this is actually a 30, 60, 90 triangle. Opposite the 60, we've got a square root of 3 on the side when the hypotenuse is 2, and the angle or the side length opposite the 30 is a 1. So it's a 1, 2 square root of 3 triangle. It's one of those that we memorize. But remember, when we're in this quadrant, our x value is positive, our y value is negative, and the radius, or that distance measured from the origin, is always treated as positive. So our cosine of negative pi over 3 can be found using, remember that mnemonic from trig, SOHCAHTOA. Cosine is adjacent over hypotenuse. The side adjacent to the pi over 3 that is not the hypotenuse itself is the one that's next to it. That's a 1. And the hypotenuse is 2. So our cosine is 1/2. So our secant is 2. Did you just flip it? Secant is 1 divided by cosine. And then we're squaring that. And so we get 4 there. So this is 4 times 3, which is 12. And remember that our x value, or our dx dt, was 3 feet per second. So we're measuring our distances in feet and our time in seconds. So that tells us our dy dt at that location, that's right here, is 12 feet per second. And that's because the rate of change of y with respect to x at x equals negative pi over 3 is actually equal to 4. So this is going to be 4 feet per foot. Now you might say, don't those feet cancel? Well, yes, they do. But I want to keep them both because I want to think about this being a change in y and this being a change in x. So our y values increase by 4 units when our x values increase by 1 unit. So if we're at this location, go 1 unit to the right and 4 feet up, and that's going to be another point on your tangent line for that graph. That's just geometrically. But then you say, my y values change by 4 feet for every 1 foot change in x, but my x's are changing at 3 feet per second. So when I multiply those together, those feet for the change in x reduce, and I end up with the change in y per unit time. So that's our y values are increasing by 4 feet every second. So we get, or 4 feet, 4 times 3 feet, which is 12 feet every second. So we get 12 feet per second. Now we know the secant is 1 over cosine, and we know the cosine of 0 is 1. So this is 1 divided by 1 squared, which is 1, times 3. So we're going to get 3 feet per second here. So geometrically, the change in y with respect to x is 1 foot per foot. So for a 1 foot change in the horizontal direction, we get a 1 foot change in the vertical direction. So our tangent line is just y equals x there. But at the same time, our x's are actually changing by 3 feet every second. So if my y's are changing by 1 foot for every 1 foot change in x, and my x's are changing for 3 feet every second, the feet for the change in x reduce, and we just end up with 1 times 3 feet per second for our change in y with respect to time. Now at pi over 4, that would be a triangle in quadrant 1. 45 degrees there. Pi over 4 is 45 degrees. It's a 45, 45, 90 triangle. So the side lengths are 1, 1 square root of 2. Since we're in quadrant 1, both the x and y are positive. And so our cosine of 45 degrees, or pi over 4, is 1 divided by square root of 2. You can rationalize if you want to, but I'm about to flip it and square it, so I won't. So the secant is the reciprocal of cosine, so we get square root of 2, and then we square it because we've got a secant squared there. And so we have a 2 there. So this is 2. We have a 2-foot change in y for every 1-foot change in x. And our x's are changing by 3 feet per second. So those feet reduce, and you end up with 6 feet per second for your change in y with respect to time. Now, one thing I want you to notice about this related rates problem and similar problems is that this equation holds in the most general case. As long as we have y as equal to tangent of x, and x is a function of t and y is a function of t, and both are differentiable, we know the derivative of y with respect to t is going to be the secant squared of our x of t times dx dt. Even if we don't know what dx dt is and we don't know what x of t is, this is how our dy dt and our dx dt are related to each other. They vary this way because y is equal to that tangent of x. And this, remember, is related to the geometry. This is dy dx. So I have the change in y with respect to x times the change in x with respect to t. It's almost like those dx's cancel, and we get a change in y with respect to t. So that's true all the time. Now, we can see this relationship a little bit better if we use Desmos.com to graph points on the curve. And if we require that dx dt to be 3 feet per second all the time. So in that case, our x would be changing at a constant rate of 3 feet per second. So we're just going from one side of the graph to the other side of the graph at a constant rate of 3 feet per second. Then our y values will, our change in y with respect to time will be that 3 feet per second times that secant squared of whatever the x value happens to be at that time. But again, if we look at the problem statement, it doesn't actually tell us that that rate of change dx dt is a constant 3 feet per second. It might only be equal to 3 feet per second at that location and that location and that location. If our x of t is given by a function with a variable rate of change, well, then that horizontal, or excuse me, the vertical line representing that x value on the curve, it's going to move at a variable rate. So that's sort of a preview of what we're going to see on the Desmos graph. Let's look at Desmos now. Okay, so here's our y equals tangent of x. And I've added this slider for our t values. So as time increases, we're at different locations on the graph. Now, because the problem statement said that dx dt was 3 feet per second, I can require x to equal just a function that has a derivative of 3 all the time. Well, you say, well, what function has a derivative of 3? Well, it's just a linear function. If it was y with a derivative of 3, we'd see y equals 3x plus some constant b, right? The slope is 3. So instead of having y as my dependent variable, I've got x as my dependent variable and t as my independent variable. So I'll just have x equals 3t instead of y equals 3x. Because we're using a different independent variable, t representing time in this case and x representing that horizontal distance. So as time increases, if we just look at not the point, but look at the line itself, it's moving across the screen at a constant rate. Might be a little bit easier to see that that's at a constant rate if we suppress that point there. So that orange line is moving across the screen at a constant rate. But if we look at the point, we can see that the y values are changing at a variable rate. If I graph the corresponding horizontal line, y equals tangent of our x value, which I've defined to be 3t, we can see that that green horizontal line is moving at a variable rate. It goes very fast, then it's slow, then it's very fast, right? And it does that for every branch of your tangent function. And so, well, what is that relationship? How is the rate of change of that x value with respect to time related to the rate of change or the y value with respect to time? We said, well, it's the rate of change of the y value with respect to time is that dx dt, or excuse me, that dy dx, which is the derivative of our tangent function as a function of x times the dx dt. So if we want to, we can graph that function. And at this point, I think it's helpful to pause our little sliders. Sometimes they can be distracting. And we see the secant graph. And I think when we look at this secant graph, it makes sense that our dy dt, that rate of change of y with respect to time, is given by this function. Because we know if we play the slider again, or play the like a t value again, I don't remember what you'd call that. But it was very fast, and then slow, and then fast. Fast, slow, fast, fast, slow, fast. And where is it slowest? Near that 0 point for each branch of the tangent function. So as we get close to this 0, our slope or our rate of change of y with respect to time is at a minimum. But then as we get farther from that, it gets faster. And that rate of change is, again, proportional to, well, it's 3 times the function value for the secant squared of x. So when that secant value, that secant squared of x value is very large, we're taking a very large number and multiplying it by 3. When that secant squared is just 1, we're taking that a 1 and we're multiplying it by a 3. So we get a slope of 3 in the middle. That's going to be the minimum slope. And then the rest of the time, that slope is going to be greater than 3. And we're going to have a slope that's very, very large as we approach each of the asymptotes on the left and the right. So it's going to be very fast, and then it slows down to 3, and then it's very fast. And we can see that if we graph it. I hope that you can see now the relationship between the y values on that white graph, which is our secant squared of x graph, and the rate of change of the y values on the teal graph. Now, the equation that we wrote down said dy dt equals secant squared of x of t, whatever x of t happens to be, times dx dt. Now, the way I've drawn this, I want to get rid of that point again. We have required dx dt to be that constant 3 feet per second. So if we just look at the orange line, it's moving at a constant rate. But what I want you to see about the work that we did earlier is that it doesn't have to be a constant rate. I hope you guys can see this. That dx dt might be equal to 3 at just particular times, at only particular locations and particular times. So if x of t happened to be t cubed, well then our dx dt would equal 3 sometimes. We'd compute x prime, just using the power rule, we get 3 times t to the 1 less power, so that's going to be 3 times t squared. That will equal 3 at t equals plus or minus 1, right? We divide both sides by 3 and then take the square root, t squared equals 1 when t equals plus or minus 1. So we'd have 2 particular t values that give us that rate of change of 3. In that case, with this modification, our dy dt would be secant squared of the x value, which is t cubed, times the derivative of the inside by the chain rule. That's our 3t squared. Now this would only give us a rate of change of, or a dx dt of equal to 3 at t equals plus or minus 1. But at t equals plus or minus 1, this is, it's equivalent to what we get right here. Actually, let me rephrase that. This is a special case of what we have here. This will always be true, given that x and y are differentiable functions of t and y is equal to tangent of x. This is only true for x of t equals t cubed. So now, if I require x of t to be t cubed rather than that 3t, I will have a rate of change that varies. Our rate of change is 3t squared. So when t equals 0, we'll have a rate of change of 0. And the rest of the time, the rate of change will be positive. So our horizontal line, which is representing our x value, it's going to move to the right, but at t equals 0, it's just going to stop for a second. And then as t goes past 0, from 0 to infinity, it's going to increase and increase. It's going to get faster. And as when t equals, say, -10, our slope, or our rate of change, our rate of change of x with respect to time would be 3 times -10 quantity squared, so it'd be 300. So we'd have a very, very large time rate of change of x with respect to time at t equals -10. But that time rate of change is going to slow down. It's going to go from negative or positive 300 to 0 as t goes from -10 to 0. So basically, this is what we've got. Here's x of t equals t cubed. Now I have a t-axis. Before I didn't have a t-axis. I had an x of t-axis and a y of t-axis. There was no t on this graph at all. But as t increased, we were at different locations. This is different. This is t. This is x versus t, where t, my independent variable t, is on that axis. The derivative of this is 3t squared. That's going to be a derivative of 0, so it's not moving. The x value is not changing at t equals 0. And the speed, the change in x with respect to time, is going to be very large the farther we get from t equals 0 on the left or the right. But it's always positive except for when it's 0. Let's see what that looks like when we're talking about the x of t, y of t plane, where there isn't a t-axis at all. So here is the graph from before, where our dx dt is 3 feet per second. So we see that that horizontal line is moving at a constant rate. Now let's change the rate of change by requiring x of t to be something else. To do that, I'm using x new as my function, or my variable, and then the independent variable, I'm using t sub 1. And this green dotted line represents my x value. Notice that the green line is always moving to the right. That's because that rate of change of x with respect to time is always positive. So our x values are always increasing, except for at t equals 0. At t equals 0, the dx dt is 0. So that's why it pauses there at x equals 0. So it goes very fast until we get to 0. It slows down at 0. And then it starts speeding up. And you say, okay, well, what happens to the corresponding y value? Well, I want my y to be equal to tangent of my x value. My x value was t cubed. Look at how the y values are changing. See, oh my goodness. It's very busy, isn't it? Let's look at the points. Right. Okay, so I don't know if that's particularly insightful. Okay, but maybe we said at t equals plus or minus 1, our rate of change of x with respect to time is 3. So let's plot those 2 points. We'll label them. And so our change in x with respect to time is 3, and our change in y with respect to time is that secant squared of 1, secant squared of our x value. But we're going to multiply that value by 3. It's going to be the same at plus and minus 1. And of course, secant of -1 is actually the same as secant of +1. So you get the same value on the other side. So our rate of change of y is going to be this 3.426 times that extra 3 at those locations. So that is what? 3 times that value, about 10.27 or 10.28. So our y values are changing by 10.28 feet per second, provided that our x values are measured in feet and our time is measured in seconds. Of course, the time units that I'm using here on Desmos are not exactly seconds, but everything that we're doing is proportional, or everything that we're seeing on the graph is proportional to the correct values. So yeah, maybe I'm not using seconds, maybe I'm using some other weird units of time, but when our rate of change is constant, we see a horizontal line moving with a constant velocity. When our rate of change varies, as in this case, where our rate of change of x with respect to time is at 3t squared, where it's fast, and then it's slow, and then it's 0 at 0, and then it speeds up again, then we see that happening with the horizontal line on the graph as well. The y values change at a varying rate that's proportional to the, well, it's not proportional. The y values change at a rate of secant squared of x times that dx dt. Since dx dt is changing, the y values are changing at a variable rate, but at these locations, t equals plus and minus 1, which correspond to x also equaling plus and minus 1. Our y values should be changing at a rate of 3 times secant squared of 1 feet per second. So this 10.28 feet per second. Let's look at the graph. Let's watch it move and see if it does what we expect it to do. So 10.28 feet per second as we're crossing those points. Might be easier to see that on the interval from just negative pi over 2 to pi over 2. Now, it might be particularly insightful if we look at the tangent line at this location. So we can say y equals the tangent of 1, that's the y value, plus the secant squared of 1 times 1 minus, or x minus 1. That's our tangent line at that location. Got a lot of extra points here. Now the slope of that tangent line is equal to that 3.426. So the change in y with respect to x is at 3.426. As our x values increase by 1 unit, our y values increase by approximately 3.426 units, or exactly secant squared of 1 units, which is approximately 3.426. Now, if our x's are changing with respect to time at a rate of 3 feet per second at that location, then we take that 3 feet per second and we multiply it by that 3.426 feet per foot. So our y is increased by 3.426 feet for every 1 foot increase in x. Well, if our x's are increasing at 3 feet per second, you multiply across, the feet cancel for the x's, and you end up with this 10.28 feet per second change in y. I hope that makes sense. I thought that the tangent line would be insightful, but it's not particularly insightful because of the tick marks on our graph. But remember, this secant squared is actually giving you the slope of that tangent line. All we're doing is taking the slope of the tangent line and multiplying it by 3 to get the time rate of change of y. Yeah, that's interesting. I'm wondering if there's something wrong with the graph. Because we know that dy dt is secant squared of x times dx dt. At x equals 0, secant squared of 0 is 1. So we should have a rate of change of 3 in the x direction or a time rate of change of 3 for x. Oh, no, that's wrong. Sorry, I was going to say time rate of change of 3 for x and a time rate of change of 3 for y at 0, 0, but that's not true because the time rate of change in this case is 3t squared, and at t equals 0, the time rate of change of x would be 0. So we're going to get 1 times 0, which is 0. So they should both slow down near t equals 0. And they do. All right. So it's kind of weird, but I thought it was kind of cool. It's kind of neat to think about how those time rates of change are related to each other. But the whole point of this video is to show that if I've got a moving point on a curve given by y equals tangent of x, the derivative of y with respect to t is related to the derivative of x with respect to t. That's why we call it a related rates problem. And this is a specific example of the chain rule. So the change in y with respect to t is the change in y with respect to x. So it's the derivative of the outside function evaluated at the inside function x of t times the derivative of the inside. But this is geometric. This is dy dx. And this is about motion. This is how x is changing with time. And if we multiply those together, we get how y is changing with time. And this is true all the time, provided that the assumptions of our problem statement are accurate. But if we're given information like dx dt equals 3 and a particular x value, we can substitute those x values and the dx dt here to get the dy dt. Or if we were given a particular y value, if we know what y is, we can take the inverse tangent of that y to get the corresponding x value. And then once we know that x value, we can substitute that into the secant squared to get dy dt as well. So if you're given either x or y, you can use the original equation to infer the other one. And then once you have the x, the y, whatever you need, sometimes you need both, sometimes you only need one of them, you can substitute those into the equation, and you can substitute the corresponding dx dt into the equation, and you can see how those rates are related to each other. But again, as we saw in the last example, it's possible that that dx dt is only true for a moment. So in this example, where x of t was equal to t cubed, that dx dt is equal to 3, but only when t equals plus or minus 1. So at t equals plus or minus 1, we have a dy dt equal to secant squared of plus or minus 1 times 3. So we get the appropriate rate of change in that case. But this formula actually works. This is just the chain rule applied to tangent of t cubed. This formula will actually work all the time. It'll tell you what the rate of change of y is with respect to time, provided that our x is changing with time, according to this equation, x of t equals t cubed. I hope that makes sense. Hope that helps. Let me know if you have any questions.